We need to learn how to name these molecules. So we've determined how to find if a molecule has a chiral center. Now we need to determine how to indicate whether or not we have mirror image number 1 or mirror image number 2. So to do that, we're going to use this thing called RS nomenclature. It's also called the Kohn-Ingold Prelog system. It's a way of assigning group priorities to determine R and S nomenclature. And it's not that difficult, but it takes a little practice. So there's going to be 4 basic rules that we have here. The first rule is going to be to assign priority to each group attached to that asymmetric carbon. Right? So number 1 will be high and number 4 will be low. How do you determine this? It's not a popularity contest. It's based on atoms with higher atomic numbers. They receive simply higher priorities. So iodine, bromine, chlorine, sulfur, so on and so forth. We consult the periodic table for this. So if we look at our 2 cases here, case number 1, let's go through this. So what do we have? We have bromine, chlorine, carbon, and nitrogen. Right, so who's number 1? Well, bromine's going to be number 1. Right, who's number 2? Well, chlorine. So you got bromine number 1, chlorine comes next, that's number 2. Now we have carbon and nitrogen. So nitrogen comes before carbon, so that's going to be number 3. And then your carbon's going to be your number 4. So this will always be the very first step that we have to do. And that step's going to be simply to number 1, 2, 3, 4. Because now we've taken this big problem and we've narrowed it down kind of to that example that we did where we had 1, 2, 3, 4. We had those atoms labeled. What about the second case here? Okay, well, bromine is still number 1, right? So that's still going to be your number 1. Chlorine's still going to be your number 2. But now when we look at our atoms, we're connected to a carbon here and we're connected to a carbon here. So just right off the bat, when we look at this position, we would say that there is a tie here. Okay. Now, your intuition is probably correct because you're probably saying, well, just go down the chain. Well, that's exactly what you do. So what we're going to do is we keep moving down the chain and we look at the second atom and the third until we find the first difference. So I want to go over this with you guys in a little bit more detail here. So let's take a look at that last example. So here we had carbon, and we're going to really do a rigorous analysis of this because we're going to see in this chapter that they're going to give you some weird structures where you really have to go through and pay close attention. So down here we have our CH3, and then we had a bromo group out at us, and then a chloro group pointing back. So that carbon that I circled is our asymmetric carbon. So we want to first take a look at our first point of attachment. So our first point of attachment here to that carbon, right? So what do we have? We have a bromo group. We have a chloro group here. Right? We have a carbon and we have a carbon. So when we look at this right off the bat, again, we know that that's your number 1. We know that's your number 2. So this is going to be our number 1. It's going to be our number 2. And that's where we had that tie. So then what we do is we go down the chain. We look at our second atom. Right? So as we go down and look at our second atom, not necessary for this, right? We don't have to do it for these 2 guys because we've already made a decision with those 2. All right, and let's go through and look at it. So just so we can highlight which carbon is which. So this carbon right here, let's assign it to this position. And then this carbon here, we'll assign to that position. So now as we go through and look at those 2, that carbon that's green, and I'll write this out in green right now, that position right there, that's connected to a nitrogen. It's connected to a hydrogen and a hydrogen, right? So as we look at it, we have a nitrogen and then a hydrogen and a hydrogen. Right? We don't need to look this direction because they're all going to be connected to a carbon down there. And then this carbon right here, that carbon is going to be connected to what? That carbon is connected to an H, an H, and an H. So then when we look at our point right here, we can see that nitrogen beats hydrogen. So that's going to be our number 3, and that's going to be your number 4. So that's your 3 up here, and that's your 4 down here below. All right, so again, first goal is to just get our numbering in. Now we're going to see some situations in which we have carbon-carbon double bonds or carbon-oxygen or carbon-nitrogen double bonds. And we're going to have to figure out a system for dealing with this. And there is a system. So let's take a look at it. So when we look at this molecule here we have our carbon-carbon double bond. And we're directly connected to an R group and an H group, and then an H and an H. So that's this R group, that's an H, and an H, and an H. So that's easy to determine. And the carbon that we're looking at right here, if we look at this carbon, that carbon is also connected to a carbon. So it's connected to this, but it's also connected to another carbon, right? It's a double bond. It's carbon once and then carbon twice. So we're connected twice here. So the way we count that is a carbon-carbon hydrogen, right? And same thing, if we're looking at this atom right here over on this side, the way we would count that is it's counted by saying, well, that's connected to an H, and then a nitrogen, but also another nitrogen, right? So kind of we get this phantom nitrogen coming down here, and this kind of ghosted or phantom carbon coming down like that. So that's what we do when we count that out. We kind of open it up. And we'll get some practice doing that as we go through some examples. So now what we want to do is we want to place here the lowest priority group, number 4, pointing away from us. And then we're going to connect 1, 2, and 3. And if we move in a clockwise direction, we're R. And if it's moving in a counterclockwise direction, then we would be S. So looking at that, here's an example. And let's just take the atoms out. Here's number 1. We'll put this as number 2. Put that out as number 3. And then that would be your number 4. So the first thing to check is number 4 pointing away. It is. It's pointing away from us. And now what we're going to do is we're going to connect 1 to 2 to 3. Right? So it's moving around like that direction if you just keep going. Okay? And that direction right now is counterclockwise. So that would be an S version of this molecule. Now, what about its mirror image? Well, let's look at it. We already know that this is a chiral carbon. So there's our carbon here. Here's number 1. And number 2 would be pointing back this direction. And then number 3 is here. And then number 4 is there. Right, so is number 4 pointing away? Yes, it is. All right, let's move around now. So 1 to 2 to 3. So it's moving around this direction right now. So that is clockwise. So that is the R conformation of this stereocenter. Now, it turns out there's a pattern with this too. So the number of stereocenters is something that can be calculated because it's just a matter of configurations essentially. So molecules can contain more than one stereocenter. We saw that in some previous examples. In general, a molecule with n number of stereocenters can exist as a maximum of 2 to the n stereoisomers. Now, a side note, it can be fewer than the maximum because of something called meso. So we're not going to get into meso for a little bit longer. All right, we'll discuss that a little bit further in one of our future discussions here. So if we look down here below, if n is equal to 1, then 2 to the 1 is equal to 2. So the isomers of that would be in R, and then the mirror image of that would be in S. If you have 2 chiral carbons, then your possibility, the max, by the way, this is the maximum number, would be 2 squared, which is 4. And the possibilities here would be R and R. The mirror image of that would be S and S. R and S. The mirror image of that would be S and R. Right? 3 would give us 8, so on and so forth.